All right, welcome back for those that are watching on video, otherwise, we've been sitting in class and we haven't moved. We are doing 3.3. This is derivatives of exponential functions. And inverse functions. So to do this, we're gonna need increasing or decreasing functions. Increasing or decreasing functions. Have this trait. An increasing function is always going up. Even if it's very slowly. And that means the derivative is always positive. And decreasing functions are always going down. Which means the derivative is less than 0. An example of the first one. Y equals e to the x. And an example of the second one. Y equals e to the negative x. Examples. Increasing and decreasing examples. If a function is always increasing or always decreasing, these functions are said to be one-to-one. I.e., for each x, there is only one y. And for each y, there is only one x. And these functions have inverses. These functions f of x have inverses. F inverse of x. And since we're doing calculus, F inverse is differentiable. At all values of x. In the range of f. Because the range of f of x are the y value, range of f of x are the y values. And these are the x values for the inverse. That's how inverses work. We swap x and y, so the range becomes the domain of the inverse. And the following thing is the worst fucking notation ever, and I'm gonna show it to you in case you like it. In case you're one of those broken few that thinks this is a fucking grand idea. But to me, it's fucking more confusing than anything. The derivative of f inverse, this is how they write it. Is 1 over the derivative of f. Evaluated at f inverse. Right? Huh? I can show you where it comes from. If we say y equals f inverse of x. This means f of y equals x. When you swap, you can do that with inverses, we do this all the time. And if we take the derivative here. We have f prime of y dy dx equals 1. So we divide both sides by f prime. And I get 1 over f prime of y. And finally. We plug y back in and y was f inverse. I don't know. I don't know how that's helpful. But if you like it. We're gonna put it through example, and I think through example is much easier to understand. So writing. This part's important. This part, meh. But increasing or decreasing functions is helpful. In fact, one of these chapters coming up, I think chapter 4 got a lot of graphing. I think it's chapter 4. Yeah, it's chapter 5 we start doing integral. Alright, you guys ready? So let's take a look at y equals p to the x, and we're gonna follow it. That pattern we just did there. What is the inverse function for an exponential function? It's the log, right? I can write this as log base b of y equals x. And now we can hit both sides with the derivative. Like this is exactly what we did right here. I'm following the steps right here. So we swap to the inverse function, we take the derivative. The derivative of this is 1 over y times the natural log of b times dy dx. And this is 1. And we want to get dy dx by itself, so we're gonna multiply both sides by y times the natural log of b. And we get dy dx equals y times the natural log of b. But y was b to the x. I don't know how many of you are gonna remember that approach. But hopefully you remember the logarithmic differentiation approach. Which we just learned a few minutes ago. Let's redo this problem using logarithmic differentiation. Take the natural log of both sides. Which allows us to bring that x down. And maybe I should, no, I don't need to put in absolute values because exponentials are always positive, so y is always positive for y equals b to the x. Take the derivative, we have 1 over y dy dx. And the derivative of that. The natural log of b is just a constant. This is kind of like 2x. If 2 were the natural log of b. Just a constant. So we're just taking the derivative of x, which is 1, it's just gonna leave the right side as the natural log of b. And we clear the fractions, we get dy dx equals y times the natural log of b, which is what we had up here. And we get b to the x times natural log of b. So either. Memorize. The derivative. Of y equals b to the x is that. Or. Do logarithmic differentiation when you need it. I'll tell you, for me, when I was a student, I memorized it, but in the long run, in the big picture, it doesn't come up often enough to remember. But logarithmic differentiation does come up more often, so this is the approach I actually remember. I will go through and do this real quick when I need it, because I don't remember that anymore. It's just, it doesn't show up often enough. But that whole logarithmic differentiation that we just spent 45 minutes doing and then some time last week. Comes up a lot. Anytime you have that x in the exponent or the variable in the exponent, it makes problems so much easier to work with. Alright, so what if we're looking at the derivative of e to the x? Now you can rework this out, or you can recognize this is y equals b to the x. If b equals e. we saw that the derivative. Of b to the x was b to the x ln of b. So we'll just change b to e here. E to the x equals e to the x natural log of e. And what's the natural log of e? That's 1. So d dx of e to the x is itself the exponential function with e is the greatest thing in calculus ever. It ignores derivatives, and you'll find out that when we do integration, it has no respect for integration either. It doesn't fucking change, it's unyielding. This is fucking crazy, because when you think about it. E to the x looks like this. And we're saying. The slope of this line, this curve right here, is exactly equal. At each point to the original curve itself. That's deep. So the slope at x equals 0 is y equals 1 there, so the slope is 1. The tangent line, if we did a tangent line here. The tangent slope would be 1. If you do it over here at like x equals 1. The slope would be e to the 1 or e. It's fucking crazy. That's kind of neat. None of you look impressed enough. Jacob's fucking falling asleep on me. That's out. No respect for the exponential function. That's one of the best things since fucking baked bread and sliced cheese. Alright. Let's kick it up a notch. You guys ready for more?
The different names for the one, the first one we did and the second one. The one we did in blue and then the one we did in green. The names, the way we worked them out.
Oh, this was doing like following the inverse method.
Okay.
And this is called logarithmic. Differentiation. Because we take the log of both sides, natural log of both sides. So that, this approach right here is take natural log. Then derivative. That's what we've been doing. All right, ready for the next problem? Y equals x squared plus 1 to the cosine of x power. Now, we are not gonna do it the inverse method, but I'm gonna show you the starting steps to show that it can be done. The inverse method would be writing this as log of base x squared plus 1 of y equals cosine x. And then using like the change of base formula. We could rewrite the left side as log of y over log of x squared plus 1. Oop, not x, cosine x. But that's all messy still. Instead. Instead, let's look at logarithmic differentiation, which is easier to remember. Differentiation. We'll take the natural log of both sides. In fact, you guys try it real quick. We've done logarithmic differentiation together a few times. You guys spend 5 minutes, 5 or so minutes, talk to your peers if you want to work as a group, and then we will do it together. I'll pause the video for a second. I never hit. All right, so I walked through that there. I didn't have a recording there. Oh, well, sorry. That's what we got there, folks. We're gonna take another break for the bathroom. All right, we're gonna continue on our exploration of derivatives, and this time we're doing inverse trig functions. I'm gonna walk you through an example of how to get it, and then I'll give you a table. But I think seeing the example is more beneficial. You understand what's going on and where it comes from. And if you understand how to do it, you can rewrite formulas for any of them easily. So let's start with just taking the derivative, find d dx of sine inverse of x.
We are still on the same 3.3,
We're
right?
still at 3.3. This is derivatives of inverse functions.
Okay.
So I'm gonna start off by saying y equals sine x, or sine inverse x. In fact, no, let's not use y, let's use theta. Because when you do the inverse function of a trig function, it's actually giving you an angle. Inverse trig functions yield angles. So we associate theta with angle from trig a lot, so let's just use that. So this is like saying x equals sine theta. Let's hit this some bitch with the derivative. I don't know why I like the expression some bitch, but it just fucking blows. And it popped in my head because we were just talking about sums. And it's literally often written SUM, some bitch, SUM bitch. So the derivative of the left side is 1. The derivative of the right side is cosine theta. And since theta is a function of x, we need to do implicit differentiation and do d theta dx. What? Are you asking me something or? Nope. Time to mute host way.
Is he not done? He can mute himself.
I don't think he realizes how much the voice carries. He's probably whispering to someone in his room and doesn't realize he's fucking right next to the speaker or microphone. Alright, so what is d theta dx equal? Yeah, I just divide by cosine theta. Got that. Now what? Well. Let's make a picture. We had x equals sine theta. So sine theta is x or x over 1. And we're gonna do some right triangle work, so we can use SOHCAHTOA. So if this is angle theta. Opposite is x. This is 1. Hypotenuse is 1. And if we don't know what this is, we could call it a. And just do a squared plus x squared equals 1 squared. Pythagorean formula. And we can find out that a equals the square root of 1 minus x squared. Here, I'm technically, if you want to see it written out, we're putting theta back in as sine inverse. You'll see that done in books, but it's not really necessary with the picture. If we've got the picture, what's cosine theta? Cosine theta is adjacent over hypotenuse, right? Square root of 1 minus x squared over 1. So it's just the top, just square root of 1 minus x squared. That's cosine theta, that's what we're sticking in there. It's the same thing there. D theta dx equals 1 over square root of 1 minus x squared. And that's what we were looking for. We wanted the derivative of sine inverse, and that's d theta dx. So. Absorbing it, Anthony, or do you have a question? So. When we're doing the trig function or inverse trig function, you can write it as an angle. Swap notations to make it a little bit easier. Take the derivative. Solve for the derivative. And if you use the swap to come up with the triangle, you can get the trig functions you need out of it. In case you've forgotten, SOHCAHTOA. Sine is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. And tangent theta is opposite over adjacent. And with those three, you can also find secant, cosecant, and cotangent, just like flipping them. Was that not neat? You guys want to see another one dry? You want to do right? Cosine, let's do cosine. I don't have it in my lecture notes to do, but this isn't all that hard. We're doing cosine inverse of x. We're gonna find the derivative of that. So if I say theta equals cosine inverse of x, what I'm looking for is d theta dx is what we're looking for. We're gonna do the old swap a root. x equals cosine theta. Get this with a derivative. And use implicit differentiation. To get negative sine x d theta dx. And so d theta dx is negative 1 over sine x. And now we make our triangle. We had x equals cosine theta, and that's x over 1, which is adjacent over hypotenuse. So if I make my triangle, x is here, 1 is here. I call that y real quick. X squared plus y squared equals 1. Solve for y, you get y equals square root of 1 minus x squared, just like when we did sine. And we want sine of x here, or sine of. Yeah. That looks weird. Sine of theta. That's what's wrong. And I want sine of theta there, and theta was this, the way I set it up, cosine was x to the adjacent side. So sine of theta is opposite over adjacent. Not adjacent, hypotenuse. Or square root of 1 minus x squared over 1. Just like we had with cosine, it's kind of neat. And so. If we put this in, this is having negative 1 over square root of 1 minus x squared. And that was d theta dx. And theta was cosine inverse. I strongly recommend while you're doing this homework for this section, when you're doing, you have the trig functions, do the triangle approach each time. That way you always understand, you will lock in the process because you're not gonna remember this shit in a fucking year. You'll remember there's square roots, but you're not gonna remember exactly what it is. But if you do the same procedure, locking in procedures. It becomes a lot easier if you do the same procedure over and over. It'll make the homework take a little bit longer, but you'll get a better understanding of what's going on, and you don't have memorization of lane formulas. It can't hurt to memorize them to speed up the check. You know, then you'll know you had it right, but
So, there's no drawback to the triangle one, right?
there's no drawback unless you're completely crunched for time. And running out of time. Well, there will probably be an example or one on the test, but only one. So it's not like it's a whole lot of, it's not an extra lot of work to do it. If you're managing your time well, you should be all right. If you're doing integration B. Like we like to do over in the Mesa Center during Friday Night Labs, where you're like racing against other students for money. There's probably cash prizes in the integration Bs. The triangle can make you lose. Or I can guarantee you win if the other student fucks up the memorization of the triangle. Or memorization of the formulas. So, speaking of the formulas, we just showed two of them. We showed the derivative of sine inverse. Was 1 over the square root of 1 - x². And we showed cosine inverse. Was -1 over square root of 1 - x². Which feels kind of right, because the derivative of cosine is negative sine. So like the derivative of cosine inverse is kind of like negative sine inverse. Derivative of negative sine inverse. It's not, I don't wanna lock that in your head, but there's some symmetry looking there. This one shows up more often than the other two. The derivative of tangent x, tangent inverse of x. Is 1/1 + x². And if we look at their reciprocal functions, the derivative of cosecant. This is where you're like, yeah, memorizing it is not fun. The derivative of secant. Is the positive version of cosecant. And miraculously. The derivative of cotangent. Is just the negative of the tangent one. That's kind of nice. In fact, if you're really wanting to make sure you have a good understanding of these. For homework. Try deriving. Tangent inverse. And then the three reciprocal ones. Secant inverse, cosecant inverse, and cotangent inverse. You don't have to do it, but it'll help. And you'll get a better feel for it, like doing it with the base ones with. Before you start having other things in them makes it a little bit easier. Alright, you guys ready for some more problems? Couple examples where we don't have a simple X on the inside. So let's do y equals. Sine inverse of 1 - 2. I'll do the formula way in a second, but we're gonna start with the triangle. Let's do the triangle one. So this is saying 1 - t equals sine of y. And we're looking at d dt here. Because t is our variable now. Gonna give me -1 equals. Cosine of y. Times dy dt. So dy dt is -1 over cosine of y. And now we need a triangle. I'm gonna put that over 1 so I can see the opposite over hypotenuse. My angle here is the y. So if I call that x, I've got x squared plus 1 minus t squared equals 1 squared. And if I solve for x, I get 1 minus the square root of 1 minus t squared. Leave it like that. Cleaning all that up. And if we look at cosine of y, it's adjacent over hypotenuse, x over 1, or just x. That's my x. So dy dt equals -1 over that thing right there. And that's what we want. So, bam. If I were to do the formula approach to this. Y equals sine inverse of 1 minus t. I would say u equals 1 minus t. So that du equals negative dt, or du dt equals -1. And this becomes y equals sine inverse of u. So dy dt equals. The derivative of sine inverse of u. Derivative times du dx. So what was sine inverse? Sine inverse was 1 over square root of 1 minus whatever's in here squared. And I said du dx, I should put du dt here. Times -1 for the du dt. And we're gonna replace u with what we started with. U was 1 minus t, so u squared is 1 minus t squared. And you'll see the formula gets the same thing as the triangle. We got one more with tangent, we'll do it both ways, I think it's helpful to see both ways. While you're doing it, learning it. We're taking derivatives now, guess what you're gonna do in Calc 2? The opposite of derivatives, it's called integration.
I was gonna say, is it antiderivative?
No, it's the antiderivative,
Oh, it's an actual thing, I was just. throwing
yeah,
that out.
antiderivative is an actual thing. It's the really long way for saying integral, but. It's working backwards and that won't, you learned some integration in Calc 1, chapter 5, but it's on the basic shit. When we start doing like shit like this, that's in calc too. We don't do so much in one semester. You guys ready for some more fun? Alright. Let's do find. DDX of tangent inverse. The square root of x squared minus one. So I'm gonna say, I'm gonna use theta since they didn't make me use y. I like having my angle be theta. Theta equals tangent inverse of x squared minus one. And we're looking for d theta dx now. And now I can switch this around and do tangent theta equals square root of x squared minus one. And we can make our triangle real quick if we'd like. This is x squared minus one over one. I just hit a button, hopefully I didn't fuck it up. Nope, everything looks good. Alright, opposite over adjacent. Square root of x squared minus one, adjacent is one. I'm gonna call this C because we often do a squared plus b squared equals c squared. So if I do square root of x squared minus one squared plus one squared equals c squared. This is x squared minus one plus one equals c squared. So that's just x squared, which means x equals c. Technically, you get plus or minus when you're taking the square root. But we're talking about the length of the side of a triangle, which can't be negative, so c is just x. We got our triangle, now we can do the fun derivative stuff. Let me pause for a second, make sure everyone's caught up. Let's hit both sides with the ddx. So what's the derivative of tangent? Secant squared, right? So we got secant squared theta, and then this is implicit differentiation, so d theta dx. Ooh, what is this bad boy? I'm gonna rewrite this with a 1/2 exponent. So when I take the derivative, I bring the power down. Lower the power by one. And then take the derivative of the inside. If I clean that up before moving over secant squared theta. The two in the denominator and the two from the 2x are gonna cancel. If I move that x squared minus one to the bottom. With the 1/2 power, it becomes square root down there. And we have an x there. What is secant theta? Secant theta is 1 over cosine theta. So we're gonna flip over the adjacent over hypotenuse and have hypotenuse over adjacent. So secant theta is hypotenuse is x, adjacent is 1. Which means secant squared is x squared. And I'll take that and I'll substitute that back in. I've got x squared d theta dx equals x over square root of x squared minus 1.
Isn't that supposed to be x squared?
What?
On the right, on the bottom right, in the square root.
Yeah. Thank you. And just hit both sides by 1 over x squared. And we get d theta dx. One of the x's on top is gonna cancel with the one of the x's down here. And we just get 1 over x times x squared minus 1. And that's what we were looking for. That was the derivative of tangent inverse. Triangle approach does take up more space on the paper, it does, but. As long as you remember how the triangles work and your basic trig functions, it's almost an error-free approach. There's less spots to make an error, let's say. Cause memorizing some of these functions is a pain in the ass. Let's do the other version of this where we do the formula. And then we'll be done. I'm gonna go with u equals square root of x squared minus 1. So that du equals. And we just did this up here. The square root of x squared minus 1 was, rather than reinventing the wheel, x over square root of x squared minus 1. Maybe I'll write it there because you're not gonna look up later on and look at it. But now we're doing d dx of y. So dy dx equals. I rewrote this as tangent inverse of u. So I need a dy du times du dx, chain rule. And dy du tangent inverse was 1 over 1 plus the argument squared. And du dx was x times square root of x squared minus 1. So if I put u back in, I got 1 plus square root of x squared minus 1 squared times x over square root of x squared minus 1. So we look at that 1 plus square root of x squared minus 1. We know it cleans up to this, we just gotta show that it does. This is 1 plus x squared minus 1, which is just x squared. So that part is just x squared. So dy dx is gonna simplify to x over x squared, square root of x squared minus 1. And after we cancel out. We are back up to that one. Cancel on X on top and bottom, and we get that one. Notice you still kind of had to do the same kind of shit we did up here. We had to do this square both things. We did it right here. The operations show up whether you do the triangle or not. But having the triangle and knowing your trig functions like makes it easier to remember what's going on, what you're doing. And why it's working the way it does.
On that top part, why did you use dy dx? Is it just because we started with the y at the top?
Here,
Yeah, or where did that come from?
I could have used theta.
Oh,
Maybe I should have used theta. Let's use theta. That's an excellent question. I just randomly put in a y without defining y. That's fucking great. But I had theta defined up there, so we can leave it like that. I don't even know that I'm pointing to it on the screen. There it is. We had theta up there, same theta. And that's all I got for you. We'll start 3.4 on, what is it, Thursday? 3.4 is on fucking word problems. Called related rates, you're gonna love it.
Professor, can I see the one that you
Good.
Thank you.
And what else are we doing? We're gonna look at. Oh, linear approximations, I think you're gonna like related rates more than linear approximations, and most people hate related rates because it's word problems. But it's application, real life application of calculus kind of thing. GTFO, I'll catch you guys later, have a good day, I'll have test scores up presumably by later tonight. Because if you have an X squared here and an X on top here, the X's can't go on the X's.
For 37. So using the same thing that I asked about earlier.
Very good. I would do that, yeah. Cause the tangent, they give me a tangent line at the point. We could rewrite this in slope intercept form with like a. And see what we get out, and you're trying to match up. A's and B's, I would do implicit differentiation, yeah.
Okay, last one on 41. I looked at it, it looks small.
Oh shit, 41, do this on Desmos.
Okay. It just,
CAS is a computer something.